Good afternoon. Today we are here with our seminar. So the seminar today is with Professor Richard Schmalensee. We can see here. So we'll start our seminar. Remember, with our seminar, economic modeling seminars, we do the second year where we are starting with seminars. That is organized by Italian Association of Environmental Resource Economists, Fondazione Enrico Mattei, in which I'm here now, University of Brescia, and with the support of European University Institute, University of Siena, Department of Economic and Management, University of Padua, and Department of Environmental Science and Policy, University of Milan. So I remember a little bit of the first edition. So in order to remember the list of seminars we had, we started with Professor Pindyck. We have a Professor Hill in the first and Professor Zwart in the first year in 2020. After 2021, we started with Professor Toll, Professor Bergman, Professor Gollier, Professor van der Plug, Professor Gerlag, Professor Kodurik before our conference in April, and during our conference we had Professor Nordhaus and again Professor Pindyck, and we'll start in the summer with Professor Metcalf, Stevens, Professor Eakins, Professor Spence, Mendelssohn, and we'll start with here in February with Professor Kilian, and we're our next second year, so with Professor Matilinski, and the last was Professor David Stern. So the next event which we are arranging are Professor Greenstone, Professor Jeffrey Sachs, and that should be more or less July. We are now in these days we are arranging the right day, and Professor Rogoff and Professor Michael Spence. So we are also arranging other seminars that we will give you more in details. So today we have a Professor Richard Schmalensee. Professor Richard Schmalensee is a Professor of Economics Emeritus at Massachusetts Institute of Technology, Howard Johnson Professor of Management Emeritus, and Dean Emeritus of MIT Sloan School of Management. About his topics and research is researching on energy environmental policy, antitrust and regulation policy, multi-site platform businesses. Is about his biography. As usual, I cut it because it's a very long, so it's an honor to have here Professor Schmalensee. So I have captured some of the most important, according to my opinion. The list is very long. So he's a director of MIT CEPR, Center for Energy and Environmental Policy Research, a director of National Bureau of Economic Research, dean of MIT Sloan School of Management, a director of the International Security Exchange, Global Economic Group Director since 2011, National Climate Assessment Development and Advisory Committee, 2011-2014, member of the American Academy of Arts and Sciences, consultant, and also there is a long list of consultants in which I collected some of them. Consultant to the U.S. Department of Justice and the U.S. Federal Trade Commission. It also has a coordinated committee on the transition to sustainability that is more in line with our list of seminars. And also there is a longer list of editorial service in which he was editor-in-chief of Competition Policy International, and he was also board or associate American Economic Review, Journal Economics Perspective, among others. About his research, he has wrote more than 120 articles in the top journals, so Econometric, American Economic Review, Quarterly Journal of Economics, Journal Economic Perspective, Journal of Financial Economics, Journal of Political Economy, and the journals, Chinese Journal, among others. Books, chapters, books are written and edited, in which we can see that there are antitrust analysis on platform markets, catalyst code, so we have collected the last published, invisible engines, deal markets of our consumers, and markets for clean air, so we collect some of them. About his research is in the top related to the list of the ranking of ideas in research economics, regulation. You can see also a lot of papers written about antitrust, and so energy economics and environmental economics, among the others. So today we have the honor to have here, the pleasure to have here Professor Richard Schmalensee. The title of the presentation: Deeply Decarbonized Electric Power Systems, Characteristics and Challenges. Now I leave the floor to Professor Schmalensee. Before doing this, I remember that during the presentation you can write some questions in the chat, and so in the end we can send the question to Professor Schmalensee. And so I leave the floor to the professor. Thank you very much.
Thank you. Thanks for that kind introduction, and thank you for including me in this very distinguished series. Thanks for the invitation to speak. As you went through the list of past and future speakers, I'm honored to be included in their midst. So I'm going to talk about what future deeply decarbonized power systems would look like as a result of some modeling, and some of the challenges those systems pose. So I'll talk about basic features that sort of, no matter how you model them, future systems will share. Then I'm going to spend some time on the modeling work we've done in an interdisciplinary study on the future of storage, future of energy storage. It's nearly complete. We are planning the rollout for next month. So I'll talk about what we did, then I'll talk about some of the results, and then I will talk about some of their difficult implications for regulation, system operations, and market design. So let's go to basics. If we are to decarbonize economies, the IEA and everybody else says what has to happen is electricity generation has to be deeply decarbonized. There has to be a lot of electrification, which of course means more generation, big increase in electricity generation. A key feature is decarbonized electricity generation is almost certain to be dominated, depending on the region, by wind and solar. The IEA says 70% of generation globally in 2050 will be wind and solar. There will be biomass, but if you look at land use constraints, biomass will mainly go to liquid fuels. And one can hope for fusion or new technologies, the alum cycle, which is a gas turbine using combustion in oxygen that looks promising on paper, but the notion that those technologies will play a major role between now and 2050 seems unlikely to most observers. Well, this is a different system because wind and solar are intermittent, right? They're variable, they're imperfectly predictable. And because of those characteristics and the fact that they will be more important in the future than today, inspired the work being done, and I'll say more about it, as I said, on storage. But let's take a look at today. Today, this is a standard cartoon for economic dispatch in an electric power system that's dominated by fossil fuels, right? There's a supply curve. Maybe it's determined by central planning under vertical integration. More commonly, it's some sort of market equilibrium. But the notion is you have a fixed supply relationship system-wide, more or less fixed. Again, there's bidding behavior. And what happens as load varies, as demand varies, you walk up and down that supply curve. But if you think about tomorrow, it's not going to look like that. A heavily decarbonized system dominated by wind and solar generation won't have a stable supply curve. Most generators will have zero marginal cost with a lot of fixed cost, and the supply curve varies, right, with the weather. More importantly, not more importantly, but as important, weather affects demand as today, but it affects both supply and demand. So recent events in Texas in particular, but California a little bit earlier, happened because of correlated impacts of weather, extreme weather, on supply and demand at the same time. As it happened in Texas, the core effect was on natural gas. Nonetheless, you're going to see it in wind, you're going to see it in solar. Now, to deal with that intermittency, Luckily, as it happens, the cost of storage has come down, and further cost reductions are expected. And what storage does is provide a partial intertemporal decoupling. You don't have to generate at the time you use power. There's some ability to arbitrage. Now, we at MIT have, for some time now, maybe 3 years, have been working on the future of storage. And what can we say? The core activity has been engineers and scientists looking at multiple technologies. We've mostly gotten cost of generation technologies from elsewhere, but we've done a lot of work locally on plausible projections of mid-century costs of energy storage. Then a team that I was a member of has used a capacity expansion model. You can look it up. It's called GenX. There are others, to estimate optimal system investment and operations in a deeply decarbonized system. And then we'll see what the features of those optimal systems imply for policy design. So just to give you a sense, we look, and I'll be a little more granular in a minute, we look at solar PV and wind hourly capacity factor based on some fine-grained data by region, demand profiles from a National Renewable Energy Laboratory study, again, capital cost, performance characteristics for various technologies studied, fuel parameters. We're going to impose carbon constraints, carbon emission constraints in the modeling. So we're going to look at the optimal response to varying levels of carbon emission constraints. We'll see what capacity we get, total system cost, hourly operations, and on and on. We looked at 3 regions. Now, this is one of the few energy modeling studies not to do California, and one reason not to do California is everybody does California. But we looked at Texas, which is frequently studied, and for Texas, the transmission grid is sufficiently robust that it seemed plausible to treat Texas as a single zone. That enabled us to use actual hourly weather data from 2007 to 2013. So we had 61,000 plus hours of weather. Texas has good onshore wind, utility scale photovoltaics, but really not hydro. The Northeast and the Southeast, there's a little hydro in the Southeast, but not much. And there is hydro in the US, in the Northeast, both within the region and from Canada. For both those 2 areas, it made sense to have multiple regions, to model multiple regions, to look at transmission capacity between those regions, and to consider the possibility of expanding. The computational complexity of multi-regions required us to use some tricks described very briefly at the bottom to basically make up synthetic weather data so we could use 8,400 hours representative in a broad sense discussed in great detail in the study itself. And on the left of the slides, you can see, again, some of the sources, some of the assumptions. We tried to be robust and use variations, lots of runs, let me just say that. We considered technologies that aren't now commercially available and made various assumptions about which would be available at what costs. I'm obviously not going to drown you in all the results. Even the study report doesn't try to drown you in all the results, but I want to use some illustrative results and give you some of their implications. So as I said, we chose 3 regions, and this slide indicates why. We wanted variation. In the Northeast, where I live, we don't have good wind, we don't have good solar. We do have some hydro from Canada, although it's hard to build transmission to get it in. We will not have nuclear power. There's just such political resistance. A lot of the solar power is on the rooftop and is hence expensive and not dispatchable. In the Southeast, I say the Northeast, we have competitive markets. In the Southeast, we have vertically integrated utilities. Good solar, some hydro and wind. We expect a fair amount of the nuclear power now in the Southeast will be relicensed. And the politics are such that it's reasonable to assume that if it's economic, maybe even if it's not, they could build more nuclear power. Texas has good wind and solar, no hydro, as I said, a single transmission zone. We focused on 2050 to basically simplify modeling. We could do greenfield models for capacity in 2050. We retain nuclear power, some of it in the Southeast, existing hydro, and existing transmission within regions. To model, we assume perfect foresight and constant returns to scale. We can talk about the implications. I think the main implication of perfect foresight is to understate the value of storage. We had a high value of lost load because, as we'll see, there's a lot of volatility in these model systems. And to avoid a lot of rationing, we just assumed a plausible value of lost load. To be clear, we're looking at optimal systems. We're not modeling any particular market structure. Reviewers who've looked at paper submissions keep saying, well, why are you modeling Texas? Well, we're not modeling Texas. We're modeling an optimal system. And we're saying, what are the implications of the characteristics of an optimal system for design of real markets? So I will come back to this, but it seems hard to communicate. We're assuming carbon constraints. So for most runs, we have a carbon constraint, grams per kilowatt hour. The shadow price on that constraint is a carbon price. We also, of course, there's a supply must equal, cannot fall short of demand except at the value of lost load. The shadow price on that constraint is the marginal value of energy. If we were simulating a market structure that is energy only, I had no ancillary services, no capacity markets, that marginal value would be roughly the spot price. I say roughly because at some points, capacity expansion is sometimes on the margin. So it's not quite right, but it's pretty close. And for what I want to say, that little qualifier doesn't matter. All right, here's some results just to be illustrative to give you a sense of what we're doing. We called the base case where only lithium-ion storage was available. We know it'll be available at grid scale in 2050 because it's available at grid scale now. So this is pretty straightforward. You see, I'll go left to right. We go bottom to top is various carbon emissions constraints, grams per kilowatt hour, and the three regions. From left to right, you have installed power capacity of various technologies, with the code being on the far right. The key is, well, then the next graph shows you energy capacity, deliverable energy capacity. That's how much is maximally in the tank in storage. On the moving to the right, you have the results of these particular runs, how much is generated from the various technologies. The next is an important graph to which I'll return to in various forms. This is how much of wind and solar generation is curtailed, is thrown away. It is not economic, except in the no limit case in a couple of regions. It is not economic to build so little renewables that you never have too much. And in the far right, you see the system cost of electricity. So to summarize much of what goes on, well, first, if you look at the middle graph at the bottom, you see the carbon emissions from the various regions with no constraints. It's 92 grams per kilowatt hour in Texas, which has good wind and solar and uses it without any constraint at all. In the Southeast with good solar, 153 grams. In the Northeast, where we have lousy wind and lousy solar, 253 grams. And the bulk of the generation without constraints in the Northeast is combined cycle gas. So the different regions differ, which is something we wanted to get. If you look now at the 10 gram and 5 gram cases, this is using only wind and solar and some natural gas and short duration lithium ion batteries. You don't see major reliability issues. You don't see, again, look at the far right, you don't see big increases in system average cost. You end up spending more, again, going from the bottom to the top in the far right, you end up spending more on storage, it's capital cost, and much less on fuel. And you use natural gas, except in the 0 gram complete, honest to gosh, decarbonized case, because every so often the wind just doesn't blow for a long chunk of time. If you have to go to complete decarbonization, that's 0. The incremental costs, you see system average cost goes up substantially, and you're getting only a few grams out to go completely to 0. So the incremental costs of going all the way to 0 look like estimated costs of direct air capture. So, I mean, our sense is that's not sort of a plausible goal, but you can get 5 grams is not much, and you can plant a lot of trees. So we looked at a bunch of other cases. Here are three kinds of storage technologies that differ. Storage technologies differ in multiple parameters that we can talk about, but this just shows here some of the assumptions we explored with different technology groups, looking at storage cost, dollars per kilowatt hour, and power discharge cost, dollars per kilowatt. The brown is lithium ion. The green is redox flow batteries that look like they're a little cheaper, a little more expensive on power discharge cost, and a little cheaper on overnight storage. Then there are a bunch of long duration storage on the axis, the light blue, that have low storage costs for a variety of reasons. I'll say a little bit later, but tend to have high power costs. Not shown there is pumped hydro for some reason, but it's in that category. And there are a bunch of other cases that I'm going to talk about in what follows. So we looked at what happens if you make redox flow available. What happens if you make thermal storage available in addition? Thermal storage is basically technology that sounds simple. It's a large scale, you heat rocks, and you use the energy in that to heat water to make steam. Pretty cheap. Then we look at what if there's plausible demand flexibility, plausible demand reduction. What if a renewable natural gas technology that people have talked about is available? What if hydrogen plays a role? Now, if you just use hydrogen to store electric energy, it turns out not to be particularly attractive. So I'll show you right now what we did with hydrogen. We looked at, again, calibrating to West Texas, where hydrogen is in fact used at small scale, but could be used at larger scale for heat to replace natural gas. So we suppose, again, calibrate to Texas, we suppose that industrial demand for hydrogen is constant. It can be met either directly from electrolysis. You use well, either wind or solar to split water, and you could pump that to meet industrial demand, or you can use the electrolysis to pump to generate hydrogen that's put into storage, and from storage it can either meet industrial demand or serve to as a source of generation. Now, we assume demand is constant. The merit of hydrogen here is that with storage, the production of hydrogen becomes a large dispatchable load. So we're not talking about dispatchable generation, we're talking here about dispatchable load. I'm going to show you results assuming above ground storage. Underground storage is cheaper, and we generated those results, but you know, life is short. There are two cases: either hydrogen is cheap or expensive relative to electrolysis costs, and they look different, but not, I would say, dramatically, and not in ways that are easy to explain, because if exogenous supply of hydrogen is expensive, you invest more in electrolysis and you generate more electricity. So that kind of makes comparability tough. But here are some illustrative results. All right, so again, we've inverted the order. At the top is a relatively unconstrained case, 50 grams per kilowatt hour. And this is all Texas. We've run this stuff for everything, of course, but this is for Texas. So as you go down, you're at the 50 gram case, 50 gram constraint, you're making different assumptions about storage technologies that are available. So when long duration storage, and that would be importantly thermal, is available, it substitutes for gas capacity. That's not dramatic, but you get less gas capacity. And of course, long duration storage substitutes for some of the brown, which is lithium ion. It's not, with the assumptions that we were given, making these available in addition to thermal, and sorry, in addition to lithium ion, doesn't do dramatic stuff at any of these three levels of carbon constraints to a system average cost, system cost of electricity. You can save a little bit. Thermal looks particularly promising on paper. We know how to heat rocks, but it's not been done at scale, so we don't know. Again, you see that as the carbon constraint is tightened under any of these technology assumptions, you system average cost goes up. It doesn't go through the roof, but it does go up and when you get down to 1 gram, rather substantially. The other thing that happens is you get more curtailment. Again, you deal with intermittency. If there are limits on your use of natural gas to deal with intermittency, you build more storage and you build more wind and solar. And when you build more wind and solar, you get more curtailment. Now, these are non-trivial levels of curtailment. That's, you know, at the bottom, it goes up to 30% of annual generation is discarded. And even at the top, you're around 10, 15, depending on the technology assumptions. Hydrogen, it doesn't show here, but hydrogen doesn't play an important role unless, you'll excuse me, unless I'm hoping my wife will answer that telephone. And maybe she's not here, in which case I will just lose the call. Hydrogen, if you just generate it, put it in a tank and use it for electricity, is not an attractive long-term storage technology relative to some of the others. But what we did, and it is reasonably attractive here because it plays a larger role in the wider economy, and that we think is interesting to explore. If you have demand response and demand shifting, it doesn't make a big difference in terms of cost. It just substitutes for short duration storage, because most of what people assume is you can shift by a few hours when the system is under stress. Okay, so some basic strategies, some basic challenges. As we've thought about these systems and we compared them to current systems, storage performs energy market arbitrage, but we can see that storage substitutes for generation, it substitutes for transmission, and although it's not in these models, it substitutes for investment in wires and the distribution system. It substitutes for transmission because transmission is a way of linking resource areas, but transmission is also, storage is also a way to alleviate, at least temporarily, bottlenecks in transmission and distribution, particularly in growing systems. What that means is that the traditional practice of planning transmission, planning generation, planning distribution systems, sort of in silos, doesn't make any sense and will lead to inefficient results. The other thing is, we think about these systems and what they're going to look like. Nobody's got any experience in planning them or operating them. Again, no stable supply curve, hour to hour. So, you know, we have some experience with wind and solar on the margin, and sometimes a little more than on the margin, but wind and solar dominant and planning. Our sense, again, talking to engineers and power systems people, this is really going to need new software to be able to deal with these systems, not just to plan them, but to operate them. Now, it may be that regulators in the EU are more technically adept than many regulators in the US. But I will simply say that at least US regulators really don't have the intellectual horsepower, by and large, the technical expertise. This is not economic expertise. It really comes down, I hate to say this, to technical expertise to manage these transitions. And we talk about augmenting the technical capacity of regulatory agencies. Finally, in terms of planning and market design, a broad challenge is that storage in particular, but also to some extent generation, if you look at rooftop solar in Australia, or for that matter, Hawaii, storage on customer premises can perform arbitrage and other functions at the bulk power level. Especially through aggregators. At least one utility in the US is contracted with an aggregator, which in turn contracts with a number of residential customers that have storage facilities to perform frequency regulation. It's not a market, it's a vertically integrated utility, but it can contract. If it were there's no reason, if there were a market, it couldn't technically perform frequency regulation. Well, that's a bridge at least we haven't crossed. How do you enable, you know, our market operators have been charged by the federal regulator to come up with rules that let storage play in wholesale markets as appropriate. This is not a simple thing to do, particularly when there are ranges of subsidies floating around to make those markets work effectively. Going the next bridge to enable market participation by distributed providers, particularly aggregators of residential facilities, is another step and requires regulation both at the federal level for wholesale markets, and in our case at least, at the state level for retail markets. And once you think about that for a half a second, you say, wait a minute, if retail customers are going to participate in wholesale markets, which they're perfectly capable of doing, shouldn't they see wholesale prices? How else do you get efficient participation, and how else do you get efficient investment decisions? We may have that, the efficient investment decisions bridge train may have largely left as you look at the proliferation of inefficient and expensive rooftop solar. But there's more potential investment to come in most places, and this is important to think about. I will give you one simple example of the consequences of not getting the retail rates right and not relating them to wholesale rates. In a number of jurisdictions, large commercial and industrial customers pay a fixed charge that depends on how much they consume at the system peak hour. Well, that's interesting, but what it has done is to lead a lot of those customers to add storage. What's the purpose of the storage? The purpose of the storage is to hit that hour. To the extent that you can forecast it in advance, it looks like it's coming, you draw down storage to meet your own demand so you don't get hit with a coincident peak charge. Well, that's just cost shifting. That's not really, I mean, it is saving some load and it's not the worst thing in the world, but it is clearly over incentivizing storage. Okay, so these are broad challenges. They follow from everything I've shown you thus far. Let me show you, however, a very robust result and some of its implications. So I've pointed to curtailments as we've gone along. I'm talking about marginal values of energy, but again, you can think roughly about spot prices. When you are curtailing generation, you're curtailing generation with a zero marginal cost. Again, there may be some O&M cost, but to a really good approximation, it's zero. And all those curtailment spots, I showed fractions of generation that's curtailed. That doesn't map directly into fractions of hours where curtailment occurs, and I will show you that. So that means that if you're running an efficient system and you're optimizing, in the optimal runs, very low marginal values of energy will be very frequent. Now, if you think of those as spot prices, and in a way the optimization does, because in these linear models, all resources break even, a theorem that many people have discovered and we stumbled into. That means that to have all these very frequent, very low marginal values, you will have either more frequent, very high marginal values or something else to cover capacity costs. It just doesn't make any sense to have enough storage, any economic sense, to have enough storage to eliminate high prices. So let me show you some Texas results. So here's a comparison of the marginal values of energy from our modeling with the actual spot prices in ERCOT, which supplies most of Texas, for two pre-pandemic years. Again, we've done this for all three of our regions, but you can't really do comparisons in the other two regions. In the Southeast, there is no real spot price because there aren't markets, and in the Northeast, there are a number of prices and also a lot of subsidies and cross subsidies and capacity markets. Texas comes closest to looking like an energy-only market. So there are a couple of things to see. Again, we're looking at three different levels of emissions constraints, from relatively benign, certainly in the case of Texas, relatively benign, to quite serious, and a bunch of different assumptions about what technologies are available at what costs. The robust result is, and just to clarify the graph as the slide says, the bottom graph gives you the percentages of prices in the various price bands, the bands shown on the right. The top splits out the top 2%. So you can see the incidence of high prices. In the modeled results, first of all, even in the 50-gram cases, which is not that tight a constraint for Texas, there are a lot of low price hours. There are a lot of hours below $5 a megawatt hour in Texas. There aren't any in ERCOT in 2018 and 2019. There just aren't any. And there are very few below, what is that, 200, below 50. The other thing to note is as you go to the right, as you tighten the carbon emission constraints, the incidence of very low prices goes up. Why? Because you deal with the emissions constraints by building more, among other things, by building more intermittent generation. The more intermittent generation you have, the more frequently it is on the margin, and thus the more frequent are very low price, very low marginal value hours. It's a little harder to see here, but you have to have more high price hours as you increase low price hours in order, in this model, for this system to break even, for all investments to break even. Now, this is a little bit of a more granular look at those price distributions, again, at rather severe carbon emission constraints. The large boxes, we don't show all hours. The big boxes show the price distributions, the frequency distributions in the sort of load curves like distributions, the percentage of hours when the price is above kind of distributions for the 45% of hours with the highest marginal values. In all the others, the marginal values are 0. And in the 1 gram case, for instance, in more than 55%, and in the 5 gram case, more than 55% of the prices are 0, or near 0. I mean, it might be $1, because occasionally you'll find hours in which storage is charging, and that pulls the price up above 0. The inset boxes give you the highest few hours, and you say, why don't we have just 0 or value of lost load? Well, in all these cases, you have some natural gas, and it has startup costs as well as run costs. And in all these cases, there will be circumstances in which batteries are charging, and that'll pull up the cost. But as you see, this is not what current price distributions look like. The other thing that this implies is most revenues come in markets in hours with high prices. Again, this is Texas simulations. It's because we had them and we used them earlier. But this shows, this is the base case with only lithium-ion storage available and carbon emissions constraints tightening. The top shows the probability distribution, again, banded. When do these resources sell? As the emissions constraint tightens, everybody, particularly, well, wind, PV, and lithium-ion, sell more when the price is low, because there are a lot more low price hours, and wind and PV just keep generating and selling when they can. But if you go to the bottom says for what price bands do they earn the bulk of their revenue? You see, they earn the bulk of their revenue, and again, go left to right as the carbon emission constraints tighten. The bulk of their revenue is earned in higher price hours. So this means in this system, again, treating this optimization exercise as illustrative of an energy-only system, which would need to be modified. Wind earns 96% of its revenue on 36% of sales. And of course, years differ. So that's an average year, but there are different years. Gas is even more extreme. Look at once-through gas turbines. That's combustion turbines. They're run in all cases, but they earn almost all of their revenues in the few very high price hours. Okay, that's a big difference from today's system. Now, are we saying, well, obviously the way to move forward in the future is to have an energy-only market? Well, in principle, an energy-only market where, as here, the only price is the spot price of energy, and you can imagine long-term contracts that deal with risk-bearing, but everybody sees the spot price. It affects all decisions. It's all great. System stress gets you high prices, low prices. And I want to stress this, low prices encourage decarbonization elsewhere in the economy. So you need that, because if you're having high BRE penetration, the average price is up. These systems, I mean, not dramatically, but moving to wind and solar will raise price as opposed to the unconstrained case. And if you really want economy-wide decarbonization, you really want to make those low prices visible. But we're not going to have an energy-only market structure. We don't have them now. Revealed preference says not a prayer. And particularly when there's more volatility in the wholesale market, the notion that generators will earn all their money in a few hours a year, not plausible, too risky, won't finance. The notion that you'll pass those prices, even more volatile than today, to retail customers, not a chance. One competitive retailer did that in Texas, went broke in spectacular fashion, and saddled the customers who didn't manage to switch away from it with preposterous electricity bills, and the litigation will go on for years. So nobody's going to do this. So what do? If you want an efficient, decarbonized electric power system, you will have to deal with higher risk, higher marginal value risk, higher spot price risk efficiently. Now, I have a few thoughts, and I look forward to questions and discussion, because these are really, I wouldn't say half-baked, but they're not fully baked. So if you think about wholesale markets in this brave new world, there will be price caps below the value of lost loads. There will be all kinds of other things. What they will look like, I don't know. But there will, if you're going to have price caps, they're going to be more important than present, because there'll be more volatility. So you'll need them. Designing capacity markets will be harder than at present. There's a lot of work being done to do effective load carrying capacity for wind and solar generators, and these are complicated simulation exercises, and everybody has a lot of fun. I haven't seen really serious work on integrating storage into those markets. The reason is that there's a fundamental difference, right? With generators, you know their power capacity. You know how many megawatts they're capable of giving you. You may not know whether it's available, but you sort of know what they've got. Except, of course, for wind and solar, where the amount of power they can give you varies with the weather. Fossil generators, it's constant. Storage, you know the power. You know how many megawatts they can give you when they turn on, but you don't know how long they can do it, because that depends on the state of charge. So exactly how capacity markets will take into account storage, I view as an unsolved problem. Maybe an insoluble problem. I mean, you're going to have to structure incentives and state of charge and when called upon kind of price schedule. That's not easy. I think the broad question is, how do you provide capacity incentive as capacity payments without distorting decisions? In these markets, where most generation has zero marginal cost, if you pay for capacity on a per megawatt hour basis, you just start operating incentives. You get generation when the price is negative, you'll get uneconomic curtailment, you won't pass through zero prices. Ideally, it should be lump sum based on something. Per megawatt for generation, adjusted for whatever. I don't know how to do that. I don't know per what for storage, but performance requirements, and then allocated to distribution utilities. A related capacity market problem, this is to some extent just a footnote, but I think it's worth mentioning. When investment in storage provides wires-related benefits, transmission or distribution, it ought to be compensated for them. There's some regulatory discussion that says, well, we should treat storage as transmission. Well, no. And treating storage as generation is clearly wrong. I think some fundamental thinking is required here to have workable capacity markets that are going to be workable in a brave new world in which wind and solar generation dominate, and storage is critically important to meet demand. I think things are even harder at the retail level. Now, when system spot price, system marginal value varies more than today, the efficiency costs of ignoring it will rise. And again, I personally stress the efficiency cost of not showing zero marginal cost to retail customers to encourage, first of all, to encourage decentralized storage, but also to encourage electrification. My favorite example, I have a son who's blessed to live in Hawaii, and he drives an electric vehicle because you can't run out of range on the island of Oahu. He pays 20 cents a kilowatt hour to charge his vehicle no matter what. He pays 20 cents a kilowatt hour when the local utility is curtailing solar generation. Okay, that's a small tragedy. But if you want to encourage electric vehicles, you want to make the point that if you time your charging, it's free. Okay, that's the sermon. But there are two important principles that you got to think about in trying to think about how to do retail rate design in this brave new world. First, to get efficient decisions at the local level, at least at the margin, consumers have to see loss-adjusted wholesale prices. Again, particularly when the marginal values are low. On the other hand, forcing them to pay really high spot prices is just not politically tenable. We've seen that in Texas, we've seen that everywhere. So you want to get the right incentives at the margin, but you don't want to face consumers with bankruptcy. The second principle is that in decarbonized systems, most of the costs will be fixed in the short run. And you know, it's sort of basic that to avoid efficiency losses, you should recover fixed costs of that sort with charges that are fixed in the short run. I mean, you don't pay per phone call anymore. You pay subscriptions. But of course, for electricity, having everybody pay the same fixed charge, current rates, at least in the US, everybody pays the same fixed charge. It's trivial. And if you say, well, let's make that really substantial, that's politically untenable. What to do? Well, here's some thoughts, and maybe we can spend some time on them in the discussion. But it seems to me that what consumers, small consumers, large wholesale, large commercial and industrial customers would probably be perfectly happy with smart meters paying the spot price, and they love it when they can get it most of the time. But small customers are going to want, even with smart meters, are going to want insurance. And it seems to me you ought to require retailers, whether they're competitive or not, to offer insurance, to offer a menu of price caps. So you will not pay more than X. Here is your fixed annual fee for X. Here is your fixed annual fee for Y. Here is your fixed annual fee for Z. And those fees will vary among customers, as among prices, depending on their past load profiles, any other observables you can think of. But they will be fixed in the short run. If suddenly you install a swimming pool and begin to heat it day and night, then the next year you'll end up paying a higher insurance charge for the same price cap. But the notion I have is that customers would be perfectly happy to pay the adjusted for line losses and so forth. Of course, we believe in nodal pricing here in the U.S., so it would be the nodal price adjusted for line losses, but never mind. They'd be perfectly happy to pay a low price as long as it's below their contracted cap. And retailers can improve their business by automating and offering consumers relatively a menu of load control arrangements. They have no incentive to do that now. But in a world in which you are a retailer, you need to offer a menu of price caps. And oh, by the way, think about what you can do if you and they cut deals for load control arrangements. Load control arrangements are reasonably widespread, at least in the US, and they have to do with a few hours a year. We will cycle your air conditioners when it's really hot and we're in trouble, and you get a break, and we guarantee you something about your temperature and so forth. You can be much more sophisticated with smart meters. You may want to agree, for instance, not to use an electric clothes dryer certain hours. As we will all move away from gas clothes dryers to electric clothes dryers, we don't want you to use them when things are difficult, and we'll put a lock on it and give you a rate if you agree to that. So a number of possibilities. Every time I have this discussion, people say, no, there's a whole other approach, and I look forward to whole other approaches, and I will look forward to your questions and your comments, and thank you for your attention.
Okay, thank you for your interesting presentation. So related to the, so I have I've written some points that are so very interesting in order to manage all this. So not only can I say gains that come from storage, you know. So we have some problem that you have a market that is changing in order to introducing this storage. In my viewpoint, in general, working on approaching in which we have investment in uncertainty and flexibility. So in this case, one thought that I have in mind is that so in the model that in which I'm working now are models in which so far I have not storage. So the problem is how to share energy among agents in an energy community. No? So the idea is which could be the possible exchange of energy. The idea that there is a huge flexibility that is introduced by the possibility to exchange energy. So we have with this kind of prosumers. Storage could be also an added flexibility. So could be again on the one end. So in my viewpoint, so we have an increase of flexibility. So it could be a gain. On the other end, you have shown us that you have also some increase of some costs. So we have a cost in order to start investment, and a reduction in some cases of costs. So we have or better, higher variability, higher volatility. So my question is related to this point. So according to the real option approach, so the approach in which we have taken into account this flexibility, higher volatility could also imply a change in the timing of investment. So if it's possible to take into account this in order to take into account which could be the effect in the market. Second point, energy community. So maybe if you take into account the energy community in the storage system, also in the case in which you are some like a small town in which you have exchange on energy, storage could also be, can I say, a manner in order to have a small market isolated also with respect to the TSO. And in this case, also we have also inside some gains, and so a different kind of market. So summarizing, volatility could be also a gain. Energy community and storage combined could be a new different market. And so if you have taken into account this point.
So you've covered almost as much ground as I covered in my talk. So let me let me react a little bit. I think the sort of fundamental European approach to wholesale markets and the fundamental US approach give you different reactions. So the US approach, we have a day ahead, fully worked out dispatch plan, right? People bid supply functions. The system operator runs a fairly complicated program and comes out with optimal day ahead dispatch instructions. And then we wait 24 hours and then make spot market adjustments. Many people have pointed out, and I think correctly, and I think we will move away from this, that with more renewables, we need to re-optimize more frequently. We need to allow for intraday flexibility. For that to work, you need flexible generation on the system. Now, the state of California, again, which is a leader in the US, particularly in solar, has now required its utilities, and is also a leader in decarbonization, has required its utilities to add flexible capacity. But of course, the flexible capacity is natural gas. So here you are in a system that has very aggressive decarbonization goals, effectively requiring its utilities to build natural gas capacity for flexibility. Storage can do that job. It doesn't substitute perfectly for natural gas because, as I mentioned, if you look at wind data in particular, you will have long calm periods, and you don't build enough storage to get you through a week of no wind. Very hard to do, very expensive. But storage can provide flexibility and the kind of flexibility you need with more renewables is really intraday. You need flexibility to react to weather surprises. Now, there may be other sources of variability that have a longer time dimension, but that's an important one. In the European system, where you have continuous trading until the gate closes, flexibility is very important. Again, the European system can respond to surprises more flexibly than the American system because you've got trading, and as soon as traders see something happening, or generators or load, they can act in the market. And as you know, the trade-off is we are able to do nodal pricing. You can't do continuous trading with nodal prices because each nodal market is too thin. You use zonal pricing, which permits continuous trading because the zones are pretty thick, but has the costs of departing from Kirchhoff's law, among other things. So there are trade-offs, but I think the question of how we get flexibility going forward is an important one. It affects both investment decisions and market design decisions. I think the US will have to move toward designs that enable more agile responses. But I also think it's going to be important in both places not to do the simple thing. And the simple thing is, let's build more gas. Gas is flexible, what the heck? But if you want to decarbonize, that can't be the main answer. It is an answer in the short run, and it may be an answer as storage costs for a while, as storage costs continue to fall, but it can't get you to 2050. And if you're building gas in 2035 in order to be flexible, you're not going to decarbonize. Did I miss your points?
No, it's okay. Okay, now we have some questions. So I will ask to Professor Falbo from the University of Brescia if he can step in and so make the question.
Okay.
Okay.
Hi. Thank you. Thank you. Do you hear me?
Perfectly.
Okay. Thank you for your very interesting presentation. I actually have a first question, and if I have time, possibly two. Your presentation points to several issues that I also find myself to cope with the work which was concerned actually with the emission market, but the profit opportunity resulting from a deep penetration of renewables was an issue also in my analysis, and it was pretty clear many of your conclusions, and that a deep penetration was going to reduce the profitability to the entire energy sector. And in my analysis, I started to observe that a possible origin of this problem was due to the fact that our usually all around the world, basically the spot market is organized through a uniform auction. And in this way, if you put the equilibrium price with the marginal technology, you of course obtain in many situations with a larger renewable penetration, the marginal cost will be close to zero or even zero, in some cases even negative, of course. So a question that I didn't have the opportunity to go through was, why, as a possible solution, don't we consider to quit with a uniform auction and instead adopt discriminatory auction? So different technology are offer individual prices, and you get what you ask for. And this would eliminate the zero price opportunity, because in that case, renewable supply would be forced to ask a compensation, yes, in a sense, in a competitive way, but sufficient to compensate zero cost, and every technology would ask for its own price, and in the ultimate case, the penetration would be complete. In the end, we would have no zero price.
Well, I think that is very interesting, and let me give you a couple of top of the head responses. The first is, of course, you'd have to do some sort of optimization to figure out what the differentials among the technologies should be. It's not completely obvious. The second is, I'm a purist. I sort of think marginal cost ought to drive things at the margin. What you will get is dispatch decisions that aren't economic, right? They don't. You'll do gas and curtail solar on some circumstances, undoubtedly, and that just strikes me as problematic. It'll also affect, depending on the ratios you choose, it'll affect investment decisions, which is why I said, I don't know how to really do a capacity market, but if your problem is, and I agree that this is going to be a problem going forward and is increasingly a problem in some areas today, if you can't get enough revenue in the energy market to justify, to sustain adequate investment, I would rather have it come from someplace else. I'm not a huge fan of capacity markets. The Texas device of and I'm trying to forget, I've forgotten the acronym, but the notion that you goose up spot prices when you're short of reserves for everybody, so they don't get marginal costs if the system is in stress. But I would prefer capacity markets, carefully designed if we can do it, to a system that basically treats different technologies differently, solely for the purpose of budget balance. So I say it's interesting, and this is top of the head, and maybe you'll persuade me if I've thought about it for a while, but I'm not sure, and it could solve the problem of inadequate revenues, but I'm not sure it's the right way to solve the problem. So, but again, I hadn't thought about it much. That's just top of the head. You had a second question. If yes, Sergio lets you do it.
If you have time, when you say that the market should guarantee a minimum level of revenues, minimum level of price, Well, it in a sense implies that there is a way to command and control in a central way how much should be invested, how much should be control. I mean, yes, basically invested in storage, or in the case of capacity, how much dispatchable technology should be in place to guarantee safety, the safety of supply. But well, how do you think to be able to control by central authority the decision which are left to the private decision, private investment? And
well, we do that in the U.S. every place except Texas, and Texas is of course Texas. But every place else in the U.S. there are either capacity markets, as in New England, where New England says, the system operator says, here's how much we're going to need, bid to supply it a few years in advance, or in California, where the regulator says, you, California, Southern California Edison, have to have this much firm capacity under contract. Where do they come up with it? Well, they do some central planning. And I've even heard Europeans talk about hybrid systems in Europe, where investment decisions have an administrative or regulatory thumb on the scale, and operating decisions are mostly market-driven. And I have the feeling, until we move to really experience with deeply decarbonized systems, it's going to be hard to get away from a lot of administration / regulation. You know, as I said, I have a son in Hawaii, and they have a lot of solar power, so I follow them with interest. That's a vertically integrated utility. It's old-fashioned integrated resource planning. The utility sits down with the regulator and negotiates. How much do we get to build? How much do we need? What's the reliability constraint? You can get an answer that way. It's not a market answer, but you know, it's not a market answer in New England either, when the independent system operator says, here's how much capacity we need, bid for it. So I have the feeling we are going to spend a lot of time in the future in worlds in which administration and regulation is important, in part because it's a brave new world. You know.
Okay, thank you very much.
My pleasure. Thank you. Good questions.
Thank you, Paolo. And now I leave the floor to Alessio D'Amato, the President of Italian Association of Environmental Resource Economists. Should be ready. Alessio, okay, here. Okay, the floor is
Hello, good to meet you.
Good evening, can you hear me?
Yes.
Glad meeting you, and thanks a lot for this inspiring talk. I'm not an expert in the electricity market, so I apologize in advance if my questions, especially the second one, might look naive in some way. But I have two, one comment and one curiosity. The comment is about the possible solutions to the problems of inequality related to the retail market changes that you were suggesting, because clearly, as you have suggested, the increasing volatility has to be dealt with to make it sure that final consumers are, that there are no problem of related to income distribution. But I was wondering, one of your suggestions is related to the possibility of retailers to offer menus of price caps depending on consumption and capacity. I was wondering if this may be a problem if we get to the conclusion that the poorest parts of the population are also the less educated or the less environmentally conscious, because it could be very difficult even for an educated person to manage a menu of contracts dealing with consumption price caps. And I think that for an average person, it could be impossible. And the second is a curiosity. I'll be very quick. If your model also allows to say something about future development in terms of waste production related to the decarbonization? Because we know that one of the arguments that are increasingly provided as problems with the decarbonization is that this is the change in the composition of waste that is due to the decommissioning of, for example, renewable energy plants or energy storage plants.
Well, first your comment, I agree with your comment. I have always been a skeptic about the benefits of retail competition in electricity under current systems, because for most households it's a small fraction of consumption, of spending, and so the incentive to actually invest the time and energy. I learned a few months ago that I'm paying more than the least possible cost of energy, because when we moved into our current residence, my wife got some competing retail offers and picked the wrong one. So does it matter? No, we don't use much electricity. But your point about the less educated is absolutely right. I'm a believer that can be dealt with, but I don't think it can be dealt with perfectly. And I don't have a response to it. I do know, and maybe you use lifeline rates for people with low consumption. We do a lot of that with telecom and so forth. It needs to be dealt with. Let me just say you raise a very good issue. The second, the study we're doing, the study we're on about storage doesn't deal explicitly with recycling and waste cost. We talk about it a little bit, but we don't model it. And we sort of put it on the board as something that has to be dealt with. What's the right regime for recycling? You want to avoid toxic materials to the extent you can, but I don't think this has been dealt with adequately. Do you make manufacturers liable to recycle? Require them to take back batteries? There are a whole set of possibilities that are being discussed, but I think haven't been pushed as far as they need to be pushed. So, two good points. Thank you.
Thanks a lot.
Thank you, Alessio. Thank you. Now we have a question from Emanuele Ciola, he's a researcher from Fondazione Enrico Mattei, that is here. Okay, now Emanuele, the floor. We are waiting.
Okay. You hear me?
Okay. Yeah.
Okay.
But we are not able to see you, but we are able to hear you.
No, it doesn't allow me. So, thank you for your interesting presentation. And it's just a curiosity about the fluctuations in the spot price of electricity due to this problem with the technology. And I'm wondering if looking at the insurances to produce insurances for consumers to control this fluctuation in the spot price, and also I'm just thinking if the problem is more a financial problem or it's a real problem. So even if we can consider and introduce some insurances in the to control the fluctuation in the spot price of consumers, if there is no space in the market for financial intermediaries to enter, so there are no profits that they can gain from issuing this type of insurances.
Well, it may be absolutely right. I mean, my friend Frank Wolek at Stanford talks about sort of elaborate regimes, and you can read some of his writing on this, of forward contracts and hedges and various sorts of arrangements. And you can certainly work it that way. That can certainly do the job. I would say first, consumers don't really need hedges against low prices. What they need to worry about is high prices, which is why I focused on insurance against high prices. Those could be offered by intermediaries, need not be offered by retailers. Absolutely right. But I don't want to be too paternalistic. I think it's sort of important not to have, for a variety of reasons, equity, education, etc., not to have too many consumers be uninsured wherever the insurance comes from. Again, we saw this in Texas, right? The retailer said, we'll give you the spot price. And that was really attractive until the run-up in price, which it anticipated. And it said to its customers, switch retailers. It's going to be really expensive. And some did and some didn't. In Texas, customers who got disconnected were often much better off than customers who stayed on and paid the bills. So you're right. You're right. All the hedging in the world and all the insurance in the world could come from financial intermediaries. The question is, would it? And I sort of have the feeling, again, this is a conversation. This is not a proposal I would take to a legislature. But my sense is that you really want some sort of compulsory insurance capability, right? I mean, to drive a car, you have to have insurance of one kind or another, and you have to have liability insurance so that if you hit somebody and cause them injury, your insurance company will cover it up to a point. Uninsured drivers are a menace, not only to others, but to themselves, because you can be bankrupted if you don't have insurance. So I think you need some kind of compulsory insurance in an electricity market with very volatile prices. What's the best way to do that and to deal with the low education issue, and in fact, the fact that even for me, the search costs are high relative to the expected benefits from looking around in competitive markets for electricity. I think these are serious issues, but I don't think the solution is, let's just have prices be constant all the time. I think that gets to be, it's an expensive policy now. It gets to be a much more expensive policy in the future, particularly if you really care about decarbonizing the whole economy.
Mm-hmm. And at this point, I'm just thinking, consider that such type of an insurance would work to cover all the consumers in the market. But at that point, we are really sure that with this type of insurance, with this type of control on the financial side, there will be also an real counterpart that in some way that control the dispatch of electricity in the market. Because I'm thinking, let's assume that there is a reduction in the electricity production. You have an insurance that so prices don't goes up for the consumers, but at that point there is no electricity in the market. So even if we have this financial structure such that consumers pay a fixed cost, such that to have the investment and to ensure the providing of electricity, it's more a real problem or more a financial problem at this point? So where is the biggest problem, the biggest issue?
Well, at that point, you raise a possibility, either a system-wide blackout or rolling blackouts in which customers aren't able to consume at any price. And that's both a real problem, obviously, and it's a financial problem because, okay, what's the contract specify under those kinds of conditions? You might say the insurance contract should pay the value of lost load. Well, you know, I mean, at this point, you get into insurance regulation issues, right? Because I don't know the European system, but in the American system, states regulate insurance companies, and the main regulatory issue is solvency. They want to make sure that the insurance companies can pay claims. Well, here assessing, you know, What was the risk of a complete system blackout in Texas? Well, it wasn't zero. There were rolling blackouts. What was the risk of a full blackout? A number of observers have said they were very close. Any company that had provided insurance to consumers against that kind of event would have a significant liability on its hands, and exactly how a regulator would assess the probability of such an event. This is a brave new world, but again, you just can't get decarbonization if it costs 20 cents for my son to charge his EV when there's too much solar. We have to find a way around that problem without exposing consumers to intolerable risks. And that's the problem I intended to pose here. I won't go to the wall to defend my preliminary thoughts on a solution, but I think it's a real problem. And I think it's a real problem that we tend to duck. I've had people say, well, your son should pay 20 cents because fixed costs have to be covered. I say, no, you don't get the economy-wide problem. You want to encourage EVs. And you don't encourage EVs if you say you always have to cover the fixed cost whenever you charge your EV, no matter what's going on in the system. So, but I appreciate the questions and I appreciate the interest, and I hope you all think about these questions because I think they're important.
Okay, thank you, Manuel. So, okay, thank you, Manuel. Now we have a last question with Professor Simone Borghesi. Simone, that is from European University Institute, and now also is the President-elect of the European Association of Environmental Resource Economists. Simone?
Yes, here I am.
Great pleasure to meet you, and life is good in Florence, I expect. Yep.
Yes, not too bad. Thank you, Professor. It was very interesting to listen to your presentation, and you raised some aspects that we really care for here in Europe right now. So thanks a lot. It was very inspiring. I have just a very general question. I liked very much when you talk about the fact that we are moving in a terra incognita. That's how you call it. And indeed, I think it's incognita in technical, economic, and also geopolitical respects right now. So I was wondering how the results of your model would be affected by changing some of the hypotheses. For instance, you know, we have so high energy prices right now, how this would affect your results, or another aspect, nuclear power. You mentioned nuclear power that in the US has different approaches in different areas. As you know, there is a large debate here in Europe about the taxonomy and whether nuclear power should be part of it or not. So I'd like to know your opinion about this and the impact on your results, so to speak.
Thanks for that question. I appreciate your interest in my work on 2050, given the situation Europe is in today. But look, high energy prices in our modeling look a lot like a carbon constraint. So the effect of a carbon constraint is you find ways to use less natural gas. So it gets you there. Nuclear power is more interesting. In at least one of our regions, we anticipate there being nuclear power in 2050, which is when we're modeling. And we also expect the political environment there, things may change, e.g. Germany, but the political environment there to still be supportive of nuclear expansion. So we asked ourselves, given the cost parameters that we have, would it make sense in the Southeast to build more nuclear plants as opposed to more wind, more solar, more storage? And the answer is, except under very optimistic assumptions, cost assumptions for nuclear power, the answer is no. Now, I'd love to be wrong. I think the anti-nuclear, I don't want to say hysteria, but the anti-nuclear opposition strikes me as more emotional than reasonable, right? Germany shuts down nuclear plants because A nuclear plant in Japan was built with backup generators that got flooded. I mean, what? Germany doesn't have tidal waves. So, you know, it's a very funny thing, but I will tell you, in my region of the country, there is not the slightest chance we will build nuclear power unless there's remarkable change. You know, I would love to see small, safe, truckable nuclear plants developed and deployed. I think that would be terrific. I don't see it happening, and I don't. Again, you know, I'm at MIT. People are optimistic. People are optimistic here about fusion power, by the way. I mean, and we laugh. It's always 30 years in the future, but the advances in magnets has really been quite dramatic. And actually, serious people are talking about fusion, not commercial, but fusion positive by 2030. That's an enormous change. And if it turns out to be real and not obscenely expensive, fusion could play a major role by late in the century. But conventional fission plants in the US, and I can't speak to Europe, but in the US are very expensive because we have been unable to devise a regulatory system that makes them affordable. We don't mass produce them like the French. And B, the political opposition is awfully strong. Just in most regions, it's awfully strong. And I will simply say, the reason the Southeast, we think it is reasonable to assume that if costs were not absurd, they could build more nuclear plants, is because those are not, the nuclear plants in that region aren't merchant plants. They're regulated. Their rate of return on assets is regulated. And those utilities are very friendly with their regulators and have been for a long time. So I think you couldn't build a merchant plant in the US. You could conceive, and there's a plant under construction. You could conceivably build a plant with a friendly regulator in an area that doesn't hate nuclear power. But that's not most of the US, and it doesn't sound like it's most of Europe.
Thanks a lot.
Thank you.
Thank you very much, Simone. Okay, thank you, Professor Schmalensee. So we are now half past 5, so we've finished. So thank you very much for your time. It would be an honor. It has been an honor for your talk. Obviously, when you can come, we are invited here, and also in theme or your celebration when you would like to come. I appreciate a lot again to talk with you, and also we will keep in touch also for the next steps of our seminars. So thank you very much.
Thank you. It's been a pleasure. Great set of questions, and boy, would I look forward to another trip to Italy. It's been much too long.
Yeah. Thank you very much.
Thank you.
Thank you.